we have some container and there's a certain number of moles of gas in that container, right? The more moles I have, the more they collide with the inside of the container, the greater the pressure they create as a result. Right? So if some of those particles are polar or they start to slow down and they start to kind of join together in groups a little bit, it still might look like a gas and behave like a gas, because if the groups of molecules that have come together are only one or two or three or just a few, that's really behaving like kind of one big molecule instead of three individual small molecules. They're not coming together in groups of hundreds or thousands or millions to form like droplets of liquid. Maybe just a few small groups, they stick together due to their intermolecular attractions instead of bouncing off. Then that kind of behaves like one molecule instead of two, so we have less. It's behaving like there are fewer moles in there than there really are, and it starts to deviate from the ideal behavior, which gives me a specific direct relationship between the number of moles and the pressure. So conceptually, if I ask you about a real gas, conceptually, probably be more likely to have a conceptual question about that than a quantitative one where you have to actually plug into the van der Waals equation. But the key thing to realize there is it would be more likely to deviate from ideal behavior if the particles start to form attractions. Like hydrogen bonds, dipole-dipole, or London forces. And their ability to do that will be greater if the gases are more polar, or they have the ability to form greater quantities of partial charge due to instantaneous dipoles, maybe if they're nonpolar. Or if I'm at a low temperature, because if I slow them down on average, they are moving around slower. They don't bounce off as effectively when they collide. They start to stick together a little bit. Or if I put more moles, a greater quantity of moles of gas, then they're just closer together. They're colliding more often, so there's a chance that they might start sticking together. Or less volume. Right? So if I take this container and contract it until I've compressed the gas into a much smaller volume, but I still have the same number of moles, well, then they're going to be close enough and they're going to start to come together and start to attract. Right, so those are the conditions where you expect to see some serious deviation from the ideal gas law. If you want to know what the real pressure, volume, moles, or temperature is for a gas, and it's not behaving ideally because of these conditions, then you need the van der Waals equation rather than the ideal gas law. So on the exam, unless I say otherwise, if there's no information about whether the gas is behaving ideally or not, you can probably assume it's behaving ideally, because we saw some examples where under normal standard conditions most gases behave ideally, or at least approximately behave ideally. So you can use the ideal gas law most of the time. Obviously it's way easier algebraically to deal with the ideal gas law than the van der Waals equation. So specifically though, if I give you a question where I say a gas is deviating from ideal behavior, or it's not behaving ideally, or it's a real gas rather than an ideal gas, conceptually these are the things you want to understand about it. But mathematically you would want to apply the van der Waals equation in a situation like that. So to make your lives as easy as possible, which you know I'm dedicated to, I will make a pledge to you now that if I'm asking you to use the van der Waals equation, the only variable I would ask you to use it to solve would be temperature. So it might be a scenario where I say you have this gas, it's deviating from ideal behavior, calculate the temperature of the gas. So in that scenario, if I'm asking you to solve for temperature, that should be easier than solving for the rest of any of these other variables, because temperature only appears once in the equation. It's easy to rearrange this to cancel this stuff out and get temperature all by itself on one side of the formula. And so that means the rest is just a matter of plugging things in. So I would have to give you some information in that scenario about the quantity of the gas. So in order for you to solve this, you'd have to be given the quantity of the gas. What units might I give you if I'm giving you information about how much gas there is? I might give that to you in moles, in which case I might give you the moles, in which case you could plug that directly in here for N, anywhere N appears. I might give it to you instead, I might give it to you in grams or kilograms, right? In which case you would need to do some conversions to convert from kilograms to grams, and then ultimately from grams to moles, and you convert from grams to moles using the mass on the periodic table. So if I did give it to you in grams or kilograms, I would also have to give you the identity of the gas. You know, so if it's helium gas, or if it's argon gas, it has a different mass on the periodic table, so you use a different molar mass to convert the grams of gas into moles of gas. But you need moles of gas to plug into the Van der Waals equation. So then I would also have to give you, in addition to the quantity of the gas, I'd have to give you the volume of the container. So ultimately, you've got to get the quantity of gas into moles. You've got to get the volume into liters. So if I give you a different volume, you've got to convert it to liters. And I would also have to give you information about the pressure, and that would have to be given or convertible into atmospheres. When you solve for temperature, you would be getting a number in Kelvin, right? And the reason for that is because we're plugging in R. Anywhere I'm dealing with R, R's units are liter atmospheres per mole Kelvin. So if I'm rearranging this formula and solving for temperature, I need the liters, atmospheres, and moles to all cancel, which means I need to be plugging things in with those units in order for them to cancel. I would also have to give you, if you're dealing with a real gas, I would also have to give you A and B, those values that appear in the equation as correcting factors, given that it's deviating from ideal behavior. So then it's just a matter of plugging in and doing a little very small amount of algebra, but mostly just mathematics, dividing and multiplying the numbers in that formula, which isn't really chemistry, so you should be able to do that.